Welcome to the presentation of compaction characteristics and microstructure of expansive soil-microdust mixtures. The authors of this paper are Nwonu DC and Ikeagwuani CC from Civil Engineering Department, University of Nigeria, Nsukka. The presentation is done by Nwonu C. Introduction. Expansive soils often pose threats to civil engineering structures. This is because they have the tendency to swell during the wet season and then they lose moisture and shrink during the dry season. So this adverse swelling and shrinkage causes undue stresses to structures constructed on them. So in view of that, we often opt for stabilisation of the soil in order to improve the properties. And chemical stabilisation is one of the methods used. And in recent years, industrial waste have been adopted. They've gained recent attention and are widely applied. So for this study, we adopted an industrial waste product known as Microdust, which is a material from quarry dust that is produced after crushing of rocks. So for this study, we investigated the compaction characteristics and microstructure of expansive soil, in which microdust particles have been incorporated. The microdust particles are basically quarry dust particles that have been sieved through a fine particle sieve in order to increase the surface area and the potential reactivity. Methodology, materials and test method. The expansive soil used for this study was obtained from Adamawa State, Nigeria, at a similar location and sampling procedure as per previous studies by Ikeagwuani and Nwonu. The rich deposits of expansive soil are normally located in the northeastern part of Nigeria, so that's where we normally obtain the sample for the test on expansive soils. The quarry dust we used was obtained from Enugu, close to Ikeagwuani flyover, at a site where it was left as waste products after extraction of crushed aggregates. Then we investigated the index properties of the soil in order to classify the soil in accordance with British standard. Furthermore, we conducted compaction tests for the expansive soil and then the soil-microdust mixtures at 5, 10, 15, and 20% microdust content. So the compaction was done in order to investigate the OMC, optimum moisture content, and maximum dry density MDD of the soil-microdust mixtures in order to see how the addition of microdust affects the compaction characteristics. And furthermore, we conducted scanning electron microscopy on the soil and soil microdust mixtures at 10 and 20% microdust content. All the percentages of the microdust were done by weight of the air-dried soil. Then for the same samples, that's the samples for scanning electron microscopy, they were sealed in polythene bags and cured for 7 days under humid controlled conditions. This is to allow sufficient time for any chemical process or reaction which will take place. And after the curing, the tests were now conducted using Phenom Pro X machine. Results and discussion. Table 1 shows the index properties of the expansive soil. And from the properties, it is clear that the soil has poor properties and are unsuitable for subgrade based on Nigerian general specification because the liquid limit exceeded 50% threshold set by Nigerian general specification, and also the plasticity index exceeded the 30% threshold. Table 2 shows the oxide composition of the soil and microdust, and it can easily be inferred that the microdust is an aluminosilicate-rich material and can be classified as a pozzolana based on the summation of the aluminium oxide, silicon oxide, and iron oxide content being above 70%. The displayed figure shows the variation of the optimum moisture content with the microdust content, and it can be inferred that with increase in microdust content, the optimum moisture content slightly drops. Similarly, it can also be observed for increase in compactive effort from the British Standard Light BSL to British Standard Heavy BSH, that the optimum moisture content also showed a slight drop with increase in the compactive efforts applied. Now we can attribute this drop to the filling of voids in the soil by the microdust particles, which filled in the voids and prevented further absorption of moisture. And thus, the optimum moisture content decreased because the soil was unable to absorb more moisture. And the figure 2 displayed shows the variation of the maximum dry density with the microdust content and also the compactive effort. And it can be observed that the maximum dry density increases with increase in the microdust content and also increase in the compactive effort from the BSL to the BSH, which we can also attribute to the filling of voids within the soil, which displaced the air voids in the soil and then imparted higher density to the soil. And also possible cation exchange processes which produced friable flux, and production of such flux makes compaction expedient, and therefore is possible to impact higher energy to the soil during the compaction. So these are the things that possibly cause the increase in the maximum dry density observed. Statistical analysis of variance was conducted in order to check the significance of the variation in the optimum moisture content and the MDD observed with both the compactive effort and the microdust content. And it can be inferred that the variation of the OMC for both the compactive effort and microdust content was statistically significant at 0.05 alpha level. Then based on the F values, it can be inferred that the compactive effort contributed more to the variation in the OMC. A similar observation can also be made for the MDD, in which the variations in the MDD with both compactive effort and microdust content were statistically significant at 0.05 alpha level based on the P values. And then it can also be inferred that the compactive effort contributed more of the variation based on higher F value obtained. Now the scan electron image of the expansive soil is displayed in figure 3A, and it can be seen that the soil particles are mainly flat and in loose and dispersed form, which is likely associated with the poor strength properties which the soil has. Figure 3B shows the scanning electron microscope image of the expansive soil with 10% microdust content incorporated, and it can be seen that the microstructure has been slightly modified, and it can be observed that the soil particles are now in compact form and are looking denser, probably due to the filling of the voids within the soil, and can be associated with improvement in the properties of the soil. Similarly, in figure 3C, it can also be observed that the microstructure of the soil is slightly modified, in which the particles are showing some dense aggregation and appear to be in a compact form, which can also be associated with improvement in the soil properties. So, based on the results obtained in this study, we can deduce that statistically significant variations in the maximum dry density and OMC were prevalent, with increase in both the compactive effort and microdust content. Secondly, addition of microdust improved the soil microstructure through filling of void spaces and possible cation exchange process, which resulted in the dense aggregations formed in the soil-microdust mixtures. Finally, we can say that the microdust shows some potential for expansive soil stabilization, since it had a significant impact on both the compaction characteristics and microstructure of the soil. These are some of the references used in this presentation. That's the end of the presentation. Thank you for your time.